All right. Okay, so they want to generalize a result about point counting to the rational numbers and to higher dimensions. So very briefly, let me describe generalizing boundary pillar from Z to Q. So it turns out this is a rather straightforward generalization. So just to sketch what happens in analogy with the previous proof, so we again consider the same set of monomials, min of I comma j, at most d minus 1, I plus j is less than delta. So we call the number of monomials in the set is 2d delta plus big O of 1. And so let's call these functions f1 through fr. And now we're going to suppose, suppose that we have a bunch of rational points. Let's say we have r rational points. So with xi, yi, both rational, and let's say we have a bound on the height, the absolute height of xi and yi. Let's say it's at most t. So then, finally, let's write, we call it d for the determinant of fj of xi, yi. And so before, we used the fact that if the xi's and yi's were integers, then so are these fj, xi, yi's. And the determinant, if it's not 0, has to be at least 1. That gave us an inequality, which allowed us to prove the Bombierre-Pila theorem. So now it's almost the same thing. So we can use the fact that height, so use that height of xy is the most height of x plus height of y. In other words, just keeping track of denominators over here, what you can show is that the height of the determinant of fj of xi and yi is bounded above by t to the delta r to the big O of 1. So, in other words, the determinant of each of these fj, xi, yi's is at most t to the delta. You have r of them, so this is true. So if, so this is d, so if d doesn't equal 0, then d is at least t to the minus delta r plus big O of 1, which is t to the minus delta squared d plus big O of delta. And the important thing is that this is linear in B. So before we had something on the other side which was delta squared times d squared. So basically if you carry out the exact same argument using this bound instead of the bound bigger than or equal to 1, you get a comparable result. Okay? So I think what you get, they haven't actually write this down, but if you just work it out in the exact same way, you get that if gamma is an R squared, algebraic of degree D, and the number of rational points in gamma with height at most t grows at most like t to the power of 3 over 2d. Okay, which I don't think is optimal. So this is epsilon plus beta plus epsilon. I don't think it's optimal, but it follows immediately from the proof. So in particular, as d goes to infinity, this goes to 0. Is what we're going to use. So basically, if you have a transcendental compact curve and you count rational points on it, the same proof method gives you t to the little o of 1, which is the kind of thing we're after. Okay. The 1 from 0 to q is not that big of a deal. Okay, now it turns out we want something a little bit stronger. Even for, well, they saw this even for a priori for the modular curve, we saw that the pullback of CM points are rational points, but these quadratic irrational points. So we want to be able to talk about not just about rational points of bounded height, but also points of, say, bounded degree over Q, bounded height. And this turns out to be a more substantial generalization. So let's make a definition. So if we have k is an integer, at least 1, and x, we might as well go more general for the definition. So let's set x to be any subset of R to the n. So then we're going to define n sub k of x comma t defined to be. So let me define it a little bit differently. So x of k comma t is going to be defined the set of points alpha in x of q bar such that the degree of each alpha I is at most k, and the height of each alpha I is at most t. Okay, so if little k is equal to 1, we're exactly counting the rational points of bounded height, so we'll say bounded numerator denominator. And if little k is equal to 2, we're exactly counting irrational quadratics inside x with bounded height. And then just take n sub k of x comma t is just defined to be the size of this set. So note that no assumptions on X. We can just make the definition in this generality. Okay? So now we want to, let's say at the very least, say for X a curve inside R squared, let's say a compact curve, real analytic, that if it's transcendental, it's not algebraic, then this n sub k of xt grows at most like a power of t. Okay? So the previous proof doesn't really work. So problem with the proof. And the problem is basically the following. So if alpha is in Q bar and the degree of alpha is at most, let's say, k, and the height of alpha is at most t, and the only bound you can give with the absolute value of alpha is t to the power of k. Okay, because one intermediate absolute value could be t to the k, and all the other absolute values could be 1. And remember the definition of height, we average over all different places, and so this will only contribute t to the absolute height. Okay, this isn't so bad. If we did the same proof as before, and instead of getting this lower bound, we got this lower bound to the power of k, that would still be fine. The issue that arises is that if you look at this d, this determinant of fj xi yi like before, so this guy, all you can conclude is its degree is at most k times r. Because there's no guarantee that the xi, yi come from the same field. In fact, they probably don't. And so if you add two guys, each of degree d, you get each of degree k, you get something of most degree k squared. Okay? So the prototypical case, for each xi, yi, you are joining the square root of a different prime. So all you can say is this is a field of degree. So the square root of all those primes are joined. Anyway, so this is a very, this is clearly insufficient. If you scale this by kr, you get something super tiny, and the argument doesn't work anymore. Alright, so this is no good. The proof doesn't work for this quantity, which we care about. So it turns out that to handle quantities like nk of xt, even if we only care about curves, even for dimension x equals 1, and let's say n equals 2, we need to work with higher dimensions. Okay, so we'll see how going to higher dimensions allows us to handle this kind of thing. Okay, so higher dimensions. What kind of things can we expect to be true? Okay, so we're going to define, we're going to look at sets X and Rn, which are quote-unquote reasonable sets, which we'll define in a bit. For now, just think of like real analytic sets, stuff like that. Things that aren't y equals sine 1 over x. We'll avoid it. And so, one thing that can happen, so one issue 1, is that even if x is transcendental, x could contain algebraic varieties. Which could contain lots of, for example, let's say rational points. And the prototypical example to think of so let's look at triples XYZ, where let's just, for simplicity, we'll insist they're all at most 1, working inside a compact box. And let's say Z is equal to X to the power of Y. This is a transcendental set, pretty clearly. On the other hand, this guy contains lots of rational points. For every rational value of y, you contain the curve z equals x to the y. That contains quite a few, a polynomial number of rational points of high velocity. So if we want some statement which says that something to do with x contains subpolynomially many rational points, we have to excise all these different rational curves. Okay? And it's even worse than one might have a priori hoped, because these rational curves don't lie in a nice family. The degrees keep growing. Z equals x to the y is the degree, the denominator of y, essentially. Okay. So what's one kind of statement we could make? So here's the first sort of, in some sense, the most basic kind of statement we could make, which is still quite amazing. So we separate X into an algebraic part and the transcendental part. So what do we put in the algebraic part? We'll put sort of everything we could possibly put in here. For every connected piece of an algebraic curve inside X, we throw that to X algebraic. So X algebraic will be defined to be the union over all connected semi-algebraic curves I inside X. So basically take any algebraic curve, look at a compact piece of it, that lies inside X, we're throwing it in. Okay? You could talk about other algebraic varieties, but that's covered by the case of curves. Every variety is filtered by curves. And obviously we don't want to allow zero-dimensional things, because this would be all of X. It's no good. And then we see the transcendental part of X is just everything else. Okay, so if X is a transcendental curve, then X trans is just all of X. If X is something like this, it's kind of hard to figure out what X algebraic and X trans are. Though in this case, it's relatively what you expect. It's basically remove all the rational Y's. Okay? So in general, these guys are not, we're going to end up calling reasonable sets. They're like infinitely many components and stuff like that. Okay, so here is sort of the first version. You learn about these results. So version 1. It says, suppose X and R to the n is reasonable. And K is some number bigger than or equal to 1. No, actually let's forget K. Let's say K. We're only going to count the rational points. So then, the number of rational points inside the transcendental part of x of height at most t. So this is the n1 x grand t. So define representation. This goes lower than any power of t. Okay, so this is already a very strong result. It covers the stuff we previously talked about, and it covers lots of interesting sets inside RDN as well. And what it's saying is basically saying if you have a reasonable set X that contains many rational points, but also contains many algebraic curves, in particular enough of them to cover almost all the irrational points.
So what are some of the properties of reasonable?
So I'll spend like the whole next lecture talking about reasonable. Yeah. So we'll defer that maybe to a bit later.
Yeah.
For now, you can at least include all compact, sort of real analytic varieties. So that's, you can just keep that in your head. So however, this sort of thing has a problem. In fact, in application this comes up. So there's two issues. So this is a theorem. There's two sort of potential issues with this result. The first issue is, and this actually will come up for us in a minute, is maybe x algebraic is equal to all of x, in which case this says nothing. Okay, so what's an example of this happening? So one example might be is like x is y cross r, where y is some set inside r to the n minus 1. Right? So maybe x only has restrictions on the first word. This is sort of a silly example in some sense. But things you might be like this aren't silly. And so in this case, you sort of end up saying nothing where you really want some control over this set y. Okay, so of course you could say sort of let's just talk about y instead of x, but the idea is to identify things concretely just by having x presented to you. And the second idea is sort of x out of the removing is sort of a little bit too large. So even in this case here, with z equals x to the y, if you think about it, if you really want sub-polynomial growth, you do have to remove all the rational y's. But if all you care about is I fixed epsilon and I want growth at most t to the epsilon, then that's not true. Then after you remove sort of all the sufficiently simple y's, you will get less than t to the epsilon growth. Okay, so for example, if x equals the set of x, y, z with z equals x to the y, and 0 is at most all of these guys, so if you let xm be x minus the set where you allow y to be a over b, with a and b at most m. A, b is at most m. So we're removing something which is smaller than x out. And this is a little bit better, because this is only finitely many different curves. So it's somehow a cleaner thing to keep track of. And the number of points in xm of height at most t. So I'm not proving this, but if you really do believe that they all come from y being rational, which they do, the number of points here grows slower than t to the 1 over n. Right, y equals 1 gives you linearly many points, y equals a half gives you quadratically many points, so square root many points, and it sort of goes on and on like that. So if we just remove this finite set of algebraic curves, we already get below t to the 1 over n. So it's sort of reasonable to expect, and it's natural for applications, to expect that once you fix an epsilon, you're able to remove something which is somehow finitely talk-aboutable and still get something on the epsilon.
Like countable? Or
So I'll state a result.
Sorry, what's the notation in this n sub q?
Sorry, so this is n sub 1 is what I mean. So,
Oh, okay, so degree is less than or equal to 1.
yes, so just rational points, basically.
Oh, right.
Sorry. I should mention just very briefly that if we replace Q with any fixed number field, all the same proofs we talked about work just as well. Q is not really special in any way. Okay, here's the second version. P-level will give the result. So this isn't, I'll write it this way. This isn't actually in Peter's Bookie's paper. Peter realized that they could use number theorification, and then he wrote a short follow-up paper which presented a stronger version of the results and could be more readily used. I only mentioned that because I spent quite some time looking at the paper to no avail. Okay. So the idea is the following. So suppose you have x and r to the n. Again, reasonable. And you fix epsilon bigger than 0. Then we want to talk about sort of finitely many families of algebraic things we're removing so that the complement has fewer than t to the epsilon points. So then there exist finitely many, again, reasonable, so Wj in r to the n cross r to the m, let's say, for some fixed m. So you can think of W just a single variety, or you can think of it as a family parameterized by r to the m, of guys inside r to the m, such that for all y in r to the m, W sub y is algebraic, is semi-algebraic. We'll also define this more precisely, but basically I think of a compact piece of an algebraic curve, algebraic variety. And also Wy is inside x. Okay. This is Wjy. And Wjy here, inside x. So such that for all t, there are at most t to the epsilon. Let me write it this way. There's a set S sub t in r to the m with size bounded above by t to the epsilon, such that the set of rational points such that x of qt is contained in the union of y and st, the union is j, wjy. Okay, so let's just unwind the definition. So what is this saying? Well, it's saying we have the set X, and there exists this family wj. It's a family over R to the m, and for each point of R to the m, it gives us an algebraic variety inside X. Okay, so because this is a family, it sort of varies continuously. Some particular things like degree remain fixed, things like that. And so yeah, it's a family over R to the m, and the fibers are all semi-algebraic, and they're all inside X. Okay, and the important thing is there's finitely many of these guys. So, like, one thing to keep in mind is that the set y is a rational number. It doesn't fit into a thing like this unless we only take finitely many y's, because no two of these guys come in like a reasonable family. Okay. And such that what? Such that if you look at all the rational points in X of height at most t, they're contained inside at most t to the epsilon algebraic varieties, which in fact come from this family. Okay, so what kind of things does this cover? So let's sort of see two examples of this at work. So the first example, just to make it precise, is if we look at the surface that we're talking about.
Just getting like super confused with like the very last statement.
This one here?
Yeah, it's just that there's only finitely many j's, right?
Yes.
And somehow j, is that j or what? Oh, is
So
that
we're taking all the j's, but the important thing is the y.
Oh, that's y. Okay, I thought
Yeah,
that was
yeah.
j.
No.
Okay, I think I get it.
No. Yeah. So let me give a precise formulation. So suppose we have this x here. So what should these, and we take epsilon to be 1 over m. So these wj's should somehow be the rational values of y. Right? So what we're going to do is j will vary between what's the right way to say this? Between, so let me just, okay, so let's say 1 is at most j1 and j2, and they're also at most m. I guess I used m over there. Let's call this 1 over L. Okay. So m is going to equal 0. So each wj will parameterize a single algebraic curve. And wj inside R to the n across a point, across R to the 0, I guess, which is just R to the n. So W of sort of J1, J2 is defined as the x, y, and z such that x, y, and z is an x and y is equal to J1 over J2. Okay? So in this case, this sort of Rm doesn't really show up. We don't have families of varieties, have single varieties. And sort of the rational points in X are going to be contained just in these varieties up to t to the epsilon of them. So what ST is going to be, so ST will be the set of XY, XZ, which are at most 1, such that like Z to the R, or Z to the J1, Z to the J1, that's J2, equals X to the J1, and XZ are in Q, such that this is true for relatively small J1 and J2. So I'm just restating what we said before in this language, where we have finitely many curves. And now if we look at all the points of height at most t, this should be what st is. And the height of x and the height of z are at most t. So then it's not hard.
So, do you want for epsilon or do you...
Sorry. One second. I think I screwed up. ST is no. Sorry, I'm confusing myself. ST
Like, is this at S epsilon? I think it depends on epsilon.
Just 1 second. No. It's not your fault. So sorry. Okay, let me do this a little bit better. Let me make the sets ST. I'm being too clever here. Depend on J. And switch this union like this. Not necessary, but it's just for my own cleanup. Okay, so no. So yes, sorry. So these guys cover all but t to the epsilon points, right? And the other points are going to be contained. Are just going to be points, right. So this is almost all the w's in this case, and the other w we're going to have. Okay, let me add some notation. I apologize. Let's make this family depend on different m's. So in this case, these guys are single curves. Right, and we always have the trivial family W. So W prime, W sub, I guess, L squared plus 1. We're going to have, so NL squared plus 1 is going to be N, which is just 3 in this case. I guess N is 3 in this case, with 3 variables. And W, L squared plus 1 is in R cubed cross R cubed, and is defined to be tuples x, y, z, x, y, z, such that x, y, z are in X. Right. Sorry. So let me fix that. So what we're doing now is the same thing as before. We have these finitely many curves to catch almost all rational points, but then we still have t to the epsilon points left over. And how do we record that? We record that with the trivial family. So this is just diagonal family. It's parameterized essentially by x, and the fiber over each point is just that same point. Is over each point here, the fiber in W is either empty or is the single point. And those clearly are inside X and they're clearly algebraic. So this family you can sort of always define in Rn cross Rn. as just points which are the same in both coordinates, and they're both in x. So, well, let me finish this example so we don't erase this. Okay, so for ST, so if sort of SJ1, J2 sub T, there's, in this case M is 0, there's only one point to fiber over. So in this case, this is just all of R naught. So we're just throwing in that curve, is what it's saying. And for the final one, SL squared plus 1 sub T is going to be the points X minus everything we've covered so far. So this set Q comma T. So this is like the catch-all family, which takes care of everything we haven't taken care of so far. Okay, and then their theorem amounts to saying that the number of points here are at most T to the epsilon. Okay? That's sort of that's the content of this here. Note that if we didn't care about the size of SJT, we could just use this single family, W all squared plus 1, with only finitely many points, bounded height, so Platonic law would suffice. But because we want T to the epsilon, we have to throw in finitely many other guys to catch on sort of most of them.
Are you familiar with determinant method?
Sorry, as what?
The determinant method?
The determinant method. My familiarity of it consists of thinking that it's what I presented about Poingari Pillai.
Okay.
Yeah, so I think what that's called is this method of determining and giving this geometric lower bound, upper bound for this arithmetic lower bound for.
Yeah, because I was thinking the statement sounds so similar.
Yes, exactly that. So I think Heath-Brown actually took this idea
Right.
and he ran with it in the p-adic setting, where you can do basically the same stuff.
Right.
Just the p-adic helps with that. I don't know what he did with it from there, but that's the extent of what I know. Sorry, I feel like I confused this a little bit. So any questions about this example? All right, so I want to give one more example, which I think is easier to follow. By the way, you can see why this version implies their version 1, right? Because for all these WJs, there's two cases. Either the fibers are sort of individual points, or the fibers are algebraic curves, or varieties of higher dimension than 1. And so whenever the fibers are of dimension at least 1, you get something which lands inside X alg, the algebraic part of X. And so the only thing here which is not inside X alg is the case where these guys are individual points, in which case you have at most T to the epsilon output. This really is a more refined sort of version of their theorem. Okay, so example 2 is the one I mentioned before. It's a little silly, but let's take X to be Y cross R. And let's, just for simplicity, take Y to be in R squared of dimension 1. the same example holds more journeys than that. So then, what's our S? Well, so in this case, our M, there really is just one S, just one. So we let M J equal to 1, and W1 is inside, this is all inside R3. So W1 in R3 cross R is defined to be, so Y1, the set, sorry, MJ is equal to 2, here is defined to be this set. So essentially, what is this? Well, it's a family parameterized by y, and what's the 5-row point of y is just the line where you fix the first two coordinates to be that point, and the third coordinate is arbitrary. Right? And so in this case, what you do is you set S1t just to be y of qt. Okay, because for any point in x with height at most t, just corresponds to a point in y with height at most t, again with a third coordinate of height at most t. So essentially x is like a family of lines, and this is telling you which lines to take. So what you end up getting from here, what Peter-Wilkes result translates to for x, is just our previous result for y. At the number of points for y of height at most t, so y is transcendental in this case. Height at most t are at most t to the epsilon. Okay? Whereas notice version 1, as we talked about before, of this theorem, just tells you nothing, because xl is just all of x. Okay, so somehow, like intrinsically from x, you recover the relevant statement about y by looking at the second version. Okay? All right. Any questions? Okay, so if not, let's stop here. And so next time we'll talk about, first of all, how this result implies essentially the same result for xkt instead of xqt. And then we'll talk a bit about the proof and what reasonable means.